So, we are talking about the cantilever problem, right. So, it was something like that. If we draw the figure again. So, initially load was at this point. So, P will be shifted from here to here, this side is y, and we are taking x in that direction, right. So, x, y, p, and we got y equal to a cos kx, b sin kx plus delta. So, delta we have defined, this is delta. Now, we have to put the boundary condition, right. So, first here the deflection is 0, slope is also 0. Now, slope will be theta dy by dx. Let us take the derivative. So, it will be minus a k sin kx plus b k cos kx. Delta is a constant quantity, it will be 0, but delta is not a known quantity, it is unknown. Delta may be any arbitrary value because we have given displacement. Now, here if we put the boundary condition, so that will give, say, at x equal to 0, y equal to 0. So, we will get 0 y, this part will be a into 1, b into 0 plus delta, right, and at x equal to 0, theta equal to 0, it will be 0 minus a k 0 b k 1, right. So, here a k sin 0 is 0, cos 0 is 1. So, it is b k a k. From here we can say b is equal to 0 because k is root p by ei, some value is there. P definitely we are not interested for 0 value. So, p by ei there will be something. So, k will be there. So, b will be equal to 0 and this part became 0, and from here we can say a is equal to minus delta because this is 0 a, this is delta. So, in that equation a is equal to minus delta, b is equal to 0. So, we can write y equal to minus delta cos kx plus delta, right. So, b equal to 0, a equal to minus delta, or we can write y equal to delta 1 minus cos k x, right. Now, if we put x equal to 0, so cos will be equal to 1, cos 0 1. So, 1 1 0 means y equal to 0. If we put x equal to L, we will get the other condition. So, let us get that. Now, rather this is the equation of our deflected shape of the cantilever. So, the shape we have drawn. So, this is the equation, right. So, y equal to delta 1 minus. So, it will start from 0 and gradually it will be equal to delta, and in between it will follow a cos curve. Now, delta is any arbitrary value. We can give here 1 millimeter deflection or 5 millimeter deflection. Based on that, it will take that particular form. So, whole thing multiplied by a delta. So, that is basically the shape of the curve. Now, here at x equal to L, y equal to delta. So from there we can get some clue about the critical load and all those. So at x equal to L, y equal to delta. So if we put delta equal to delta minus delta cos KL. So it is x equal to L and delta delta if we multiply. So this delta will cancel, right? And ultimately it will be delta cos KL equal to 0. Now if delta equal to 0, it will be that straight case. So it is a trivial case, right? We know when there is no problem, load is beyond the range or load is 0, so it will be straight. We have that idea. So we are basically trying to get something else. So we have to get cos KL equal to 0, or KL will be, where cos theta will be equal to 0. At 0 it is not 0. So it will be at 90 degree, it will be 0. Again if we come this side, means 270, so it will be pi by 2. Then so it will be
pi by 2 plus n pi.
You can write so here it will be 0, here it will be 0. Again it will be 0, again it will be 0. So here it will not be 0. Right. So here it is your pi by 2, here it is 3 pi by 2. Again it will be 5 pi by 2. So if we put in an in form, so it will be at 1, 3, 5 like this. So we can write 2n minus 1. 2n minus 1. So if n equal to 1, it will be 1. If it is n equal to 2, it will be 3. So this, that we can write. Right. So this part, so there should be a factor 2n minus 1 pi by 2. The minimum value will be n equal to 1, it will be straight away pi by 2. Now if we try to square that equation, so it will be k square L square equal to 2n minus 1 square pi square by 4, and k square equal to p by I, 2n minus 1 square pi square by 4. Okay. Now if we rearrange, we will get from here, so p equal to your 2n minus 1 square, here pi square E square by 4L square. Pi square EI, pi square EI, this is pi square EI by 4L square. Or if we write in a fresh way, it will be P equal to 2n minus 1, that part if you take here, it will be pi square EI by 4L square, right? Or we can write 2n minus 1 pi square 2L square. Now if n is equal to 1, so p will be pi square ei by 4L square, or we can say pi square ei by 2L square. Now this value will be, if it is n equal to 2, it will be 9 times, right? So it will be n equal to 2. So it will be 3, 4 minus 3, 9, right? So here pi square ei 4L square, here there will be 9, or we can write 3 square pi square ei by 2L square. So in different form we can express if n is equal to 2, if n equal to 1, right? And we have the expression y is equal to delta 1 minus cos kx. Now if we put 1 minus cos k, already we have determined, so k is 2n minus 1 divided by 2 pi x. So here we got k equal to something, so we can write k equal to 2n minus 1 pi by 2l. So here 2l will be there, right? Or I think it became very small size, we can write y equal to delta 1 minus cos 2n minus 1 divided by 2l pi x, right? So that will be the expression for the deflected curve. It is dependent on your delta. So if you make it 1, you will get this shape. If it is 2, means shape will be identical, only it will be magnified with a factor delta. And the p value, it will be pi square ei by 4L square multiplied by 1 or 9, or next time it will be, I think 3, 5, it will be 25. So like this the different values you will get, but this one will be the minimum value, right? So if there is no resistance, so it will try to deflect at n equal to 1, and the value will get pi square ei by 4L square. So earlier we got how much? Pi square ei by L square. So pi square ei by L square is a very standard form. With that, if you just divide by 4, so here also if you change the mode, there is a factor multiplied. So pi square ei by L is a very unique case. So we are talking about a column, both end is hinge. If we apply, that is the basic case or fundamental case, because there the first mode value is pi square ei by L square. Other mode we are getting some factor with this, or other boundary condition, say cantilever case, for fundamental itself just it is 1/4 of that. Now we can physically correlate the two different problems, right? Now a simply supported problem. The deformed shape is a sinusoidal curve, fundamental case. Now if we take a cantilever, I think I should draw in a different way, otherwise it will not be possible to explain. From here I am drawing it. this curve was a sine curve, and that was the cantilever. That was just now the equation of what we got. So y equal to delta 1 minus cos kx, right. So it is a cos curve. So it is not directly cos curve with some minus and all those. Okay. Now we have the understanding that if we draw a sine curve like this, so if we start from here, so it is a cos curve, right. So sine curve start from 0, it will be like this. So if you start from here, so it will be right. So there is a just phase lag, and this value is 0 and this value is 1. So here you try to see, it is 1 minus cos. So the deformation pattern is more or less same. So it is represented in a sine form, that is represented in a cos form, right. Or this part also you can represent cos, we can make it 1 minus, say cos 2 theta equal to cos square theta minus sin square theta. So 1 minus 2 cos square theta. So 1 we can cancel. So it can be represented in that form. Okay. So anyway, both are a similar type of curve. Now here if we put a mirror, we will get a mirror image of that, right. Okay. So this is the cantilever. If we put a mirror here, we will get a mirror image. Now if we join it end to end, and if we compare this one with the fundamental case, so it is like this, it will be like that. So this is a sine curve, this is a cos, but I told this is, here it is like this, here it is like that, starting from higher value, a mirror image. Now if you shift the axis, say if we take this one, this is the base, and think in a reverse manner. So what will be happening? This curve is more or less same thing. So if it is L, this will be L. So here how much you got? Pi square EI by L square. Here pi square EI 2L square. So it is L and L, it is 2L. So we can write P critical equal to pi square EI by L effective square. So that is the general expression of a critical load. So pi square EI by L effective square. So L effective is equal to L for this case. In that case, L effective is 2L, right. So if we put here 2L, you will get the critical load in that case, right. So what is fundamental case? It will start from 0. So if you take a sine curve, so this is a full sine curve. So if we take a half sine curve, that will be found in a fundamental case. Now here if it is cantilever, we can take a mirror image, and that part will be more or less like this. So if it is L, so if we take 2L, 2L will be identical to that case. So in that case we say the L effective for a cantilever beam is twice L. So what is L? L is the actual length. So without deriving that equation, if we just compare the mode of buckling, from there we can make some analogy and find out the L effective value and get the value of the critical load. Now I am taking a different case now, and without deriving we will find out the critical load from that understanding. So two cases we have derived. One is a fundamental case, both end hinge. Another is the cantilever case. next case say both ends are fixed, right. So if we take both ends are fixed, say both ends are fixed and it is subjected to P. Now initially there might be a problem in the feeling that if both are fixed, if we apply load, how load will be transmitted. It is fixed means the rotation is not allowed, the vertical movement is not allowed, horizontal movement one end it may be resting, other end it should be allowed. Okay. So sometimes you will find a hinge case, both the end it is hinge, load is there, it should not pass. But here at least I have tried to make one thing is roller, so that feeling should not be there. But sometimes in some case you will find it is hinge. Both. So you have to assume that tolerance of movement is there in that case. So here also it will be there. Okay. So main idea is the movement part is allowed here. So load will be transmitted. Now if we draw the deformed shape, fundamental one, so here slope will be 0, it will be maximum and it will go like this. So here it is clamped, there will be no deflection, no slope. No deflection, no slope, it will be maximum, symmetry, slope will be 0, so shape will be something like this.
So why can't we think that it will go up?
Okay, it may go in the other way also, okay. So that part I am not interested at this level, okay. So it may bend this way or that way, okay.
This on the column, which side is the column wants to go?
Now this figure, if we divide into say let us draw the deflected shape. Say it will be something like this. Okay. Now here you can just divide. How many divisions? This is the central part. Say it is L by 2. This will be your L by 4. This will be your L by 4. Now if we put a mirror here, so at a distance of another say L by 4, L by 4. Right. So this is the original portion. Now that we have divided central part L by 2, L by 4, L by 4. So beyond the support, if we continue this curve in a mirror image form L by 4, so it will be like this. Now this part is just like a fundamental case, because here slope is there plus, and this part is also the fundamental case. So it is L by 2, this is also L by 2, this is also L by 2. Right. So there are 3 representative parts, each are having a length of L by 2, and both the end some slope are there, plus it is symmetrical at the middle maximum amplitude. And really if you solve that problem with our differential equation EI d2y dx square equal to the moment, equation you will get, you will find here at L by 4 you will get the curvature equal to 0. Normally, if we take a simply supported case, both the end bending moment are 0, means d2y dx square are 0. So, if you just solve and get the deflected curve at L by 4, your y will be there. If you take derivative, you will get slope. You will get another derivative and put L equal to 4, you will get here curvature will be equal to 0. So, if curvature equal to 0, slope is there. So, we can just assume this is a part just like this portion. So, similarly, it will be like that. So, here what will be the effective length? It will be L by 2. Yeah. So, this is representing one fundamental case. So, L by 2. So, your P critical, it will be pi square EI. No, it is pi square EI L effective square, or we can write pi square EI L square. It will be 4 above, because it will be L by 2, L square by 4, 4 will go up. Right. So, we will get 4 times the basic case pi square EI by L square. Now, fundamental case, the value was pi square EI by L square. For cantilever, it was pi square EI by 4 L square. Here, 4 into pi square EI by L square. Now, physically also we can get some feeling that if these two ends are simply supported, if we apply load, we are going to get pi square EI by L square. Now, when it is critical, it will try to buckle. Buckle means bending will be initiated. Now, if there are some fixity at the end, structure will be much more strong. If it is clamped, means slope is also restrained. So, support is much more strong. So, we should expect more strength from the structure. Definitely, your critical load wise, if you calculate, so from simply supported case to clamped case, the critical load value will be, you have to apply 4 times. So, if it is hinge case, if you apply 100 and if you get the buckling, here it can carry up to 400. So, 4 times load it will carry, because it is much more strong. And if it is a cantilever case, cantilever is very weak type, one of the end is absolutely free. So, strength is 1/4 time. So, at 25 it will fail it. Right. So, here it is all square of the effective length. Now, I will take a case where this concept cannot be applied, because if we make one end, so far the both end hinge, both end fixed, it is more or less symmetrical type of section. If we take this is fixed, this is hinge, what will be happening? It will be unsymmetrical, right? So, that is nice, deformed shape we will not get. So, definitely we have to start from the basic equation. But there also we will get something, and it can be correlated with some of the values. It is L and E and I. So, L is the length, here is the flexural rigidity, there is a force P acting here, this is XY deformed shape. Now, the problem just now we considered this one or the earlier one, the support reactions are quite complicated, because if there is a P, this side there will be a P. Now there will be a moment generated here, and this end there will be no moment. Now this moment will be balanced by some equal and opposite force. So we can say there will be a horizontal P, there will be a moment here M, because it will not try to rotate freely, automatically some moment will be generated. And if there is a moment, say P will cancel, there is no load, only moment, that moment will be balanced by this reaction force. So it is anticlockwise. So here there will be a reaction, there will be a reaction R and R. So R into L will be M. So if we know R, we can calculate M. If we know M, R we can calculate. But what will be the value, that is not known. Now in the case of fixed condition, so some moment was there at this end, some moment was there at that end. Say if it is M, it is M. Now here M should be balanced with that, so there will be no reaction. But here some reaction, some moment will be there, and it is unknown. Okay. Now this problem, it can be solved in two ways. Number one, say at any station, at x, that will be y, what will be the moment at that station? So you can come from this side or you can come from that side. So it is better if we come from this side. So if we take any station here, so this is x, that is y. So your M will be your R into L minus x, and that will be a hogging type of moment. So we are taking it as plus minus P into y. Now if we write EI d2y dx square, so it will be simply R L minus x minus P into y. Now here there is a quantity R that is not known. So if that is not there, it should be more or less like your earlier form. Now this problem can be handled in two ways. One of the option is you can take fourth order equation. If you take derivative twice, so RL will cancel in the first option, second option it will be Rx will be R, another derivative R will go there. Okay. So fourth order derivative, it will be vanishing. So we have to integrate 4 times, and we have to put the boundary condition at the two end. Here deflection 0, slope 0, here deflection 0, curvature 0 or moment 0, whatever you can say. Now problem will be much more involved because 4 unknowns, 4 equations. Another alternative, we can try with the second order keeping this R, right, because it is a buckling problem, it will be in the form of R, just like the cantilever problem there was a delta. So that part will be associated with all the equation, and finally we will get something equal to 0 and KL will be some parameter. Okay. So we can make and try, and I am hopeful we will get the result if we retain R in the system. But in other problems, say if it is a static problem, we can't solve it, okay, because it will be always in the form of R. But here our attention is little bit different. So we are not, if something multiplied with R, so let it be there. Okay. Now this EI part we can put here, and it will be your k square and rearrange the equation. So it will be your d2y by dx square plus k square y. So this part you bring here divided by ei, that will be your r ei L minus x. Now for the first part, if we consider right hand 0, we will get a complementary part. So that will be simply a cos kx, b sin kx. And right part, the particular integral, that part we have to determine. So that is, so here we can calculate, say we can calculate in this form. It is d square plus k square, again in the same form, y particular r ei L minus x. Now this part we will put on the other side. Again we will try to expand it with d square and all those. So here maximum order is x. So finally it will go on cancelling it. So this yp we can write d square k square minus 1 or this part 1 by k square we can take out, 1 plus d square by k square to the power minus 1 r ei L minus x, or we can write here this part 1 minus d square by k square r, this part is k square ei L minus x. Now this is the second derivative. If you go beyond, it will be fourth, sixth. So if we take derivative twice, this part will be 0. So first derivative x will be 1, second derivative will be 0, other part with first derivative it will vanish. So only 1 into this part will be there, remaining part it will vanish. So here k square equal to p by ei, so ei we can cancel, so we can write r, and here we can write p, and here L minus x, and it will be multiplied by 1. Other part if we take, we will not get anything. So y we can write the complementary part a cos kx, b sin kx, r p L minus x. Now this part we have to apply boundary condition. So here slope is also 0, one of the condition. So theta equal to dy by dx, that part also you find out, it may be required. It will be minus k a sin kx, b k cos kx, and this part will be minus r by p. Right. Now we have the problem. So at x equal to 0, y equal to 0 plus theta equal to 0. At other end, deflection equal to 0. So these boundary conditions we have to put. So at boundary condition at x equal to 0, y equal to 0. So it will give 0 equal to a cos 0 is 1 plus b sin 0 equal to 0 plus your r by p into L, x is 0. So you can say a is equal to minus r L by p. Now the next boundary is at right x equal to 0, theta equal to 0. So here 0 will be minus k a into 0 plus b say k b into 1 minus r by p. So here we are getting b equal to r by kp and a equal to rl by p. So we are getting both the value ab. So if we put in the expression, so y will be a will be minus r l by p cos kx, p is r by kp sin kx plus r by p l minus x, right. So ab we obtain, so a equal to minus r l by p and b equal to r by kp cos sin r by p l minus x. Now we can put the last boundary condition that at x equal to l, y equal to 0, right. Now here you see r is a common quantity, so we can take that part is common, okay. So r at least we can take common, so we don't have any problem at this level. So p, okay, it may be there, okay. So now if we put say at x equal to l, y equal to 0, that will lead to, if we put here x equal to l, we will get this one, say 0 is equal to minus r l by p cos kl plus r by kp sin kl, and this part will be equal to 0. So if we come here l, if we put here, it will be 0, it will be sin kl cos kl rl by p r by kp, so whole quantity will be equal to 0. Now here this r by r by p will take common, some k and l also we can take common, k we can take common, right. So it will be kl minus cos kl plus sin kl. So r by kp you have taken common, it will be sin kl, it will be cos kl. So r by p, k is there, l will be there, so we can multiply k here, k here. So k, now here the central part should be equal to 0. So if there are some load, r will be there, and if p is not there, so p should be at least some value, and k will be p by I. So we are not bothered about what will be the value of that. So we can write the central part, that should be equal to 0, or from there we can write tan kl equal to kl, right. We can write minus kl cos kl plus sin kl equal to 0, or sin kl equal to kl cos kl, or cos part if you take here tan kl equal to kl. Now this is one of the tricky equation. Earlier we got kl equal to sin kl equal to 0 or cos kl equal to 0, kl equal to either pi or 2 pi, something like this, or pi by 2, 3 pi by 2 something. So here kl equal to l, so it is just like x equal to tan x, right. So there is no direct solution of this, so we have to solve it in an iterative manner. So we can just put here 1, 10 KL if we 1, and you say this value is 1 or not. After that you can put say 1.1 and 0.9. You see which one is going in a better way. Or we can say 10 KL minus KL equal to 0. So we can put say KL equal to 1, and this is say some function f. For KL equal to 1, function equal to how much? Then 1.1 how much? 0.9 is how much? So it should tend to the 0. So which one is tending to 0? So like that, if you just calculate, substitute some value of KL. So 10 KL minus KL should be equal to 0. So KL you can start from say 1, then 0.9, 1.1 or 1.5, 0.5. So initially you can go with a large interval. After that it will give some neighborhood. So within that we have to refine, and we will get the value of KL. That should be equal to 4.49. It is not the exact value. If we match, we will not get identical. Small fraction will be there. So it depends how many significant digits you will pick up. So if it is KL, so we can make square. So K square L square equal to 4.49 square. So K square equal to pi by I. So it will be pi divided by I, L square equal to 4.49 square. Right. So 4.49, if we just from here P equal to 4.49 equal to 20.2. Right. I by L square. Roughly the value, you can take more significant digit. So KL equal to 4.49, pi square is L square will be square of that is 20.2. So here P by I, so if you rearrange again it will be 20.2 I by L square. Now we have the standard form pi square I by L square. What is pi? Pi 3 point something square. So that part if you take common, there will be some parameter, that parameter in an inverse form if you put below and within L. So P can be nicely represented as P or P critical, it is pi square I by 0.7 L square, right. So this 20.2 divided by pi square, if you make something you will get. So that if you put it below, it will be, you will get some 0.49 or something. Okay. So that if you put in the bracket, it is 0.7. So what is this? This is basically L effective, right. Now L effective here it is how much? 0.7 L, right. Now you come to the different cases. Here L effective equal to how much? L. This is 2L, not 2L. It was L by 2, or we can say 0.5 L. This is how much? 0.7 L. Now here it is hinge. Now if you make both the end fixed, so your L means 1.0 L. So 1 L became 0.5 L. Now if both the end are not fixed, one of the end is fixed, it is, so it should be in between 1 and 0.5. The value came 0.7. You should have happy if we put 7.5. So it is not 7.5, but anyway it will be some intermediate value. if you take 0.75, so you are going to take more effective length. So more effective length means it will be much more weak, right? So from your intuition, if you take 0.75, so you will be on the little safer side in the design, but actual value will be 0.7. Okay. So all the cases it is basically pi square EI by L effective square. So L effective it is, for cantilever it is 2L, for fundamental case it is L, for clamped it is 0.5L, clamped hinge it is 0.7L. So for single span, more or less these are very standard type of form. So that can be utilized, right. Now in the tutorial class we will carry some numerical example and try to find out, say some section will be given, what will be the limit of load, or load will be given, you have to find out the dimension of the or cross section of the member. So it will be a reverse problem, a design type of problem. Now before finishing today, the buckling part is pi square EI by, all the time we are talking about E, this P critical equal to pi square EI by L effective square. Now here direction we are not talking about, this way or that way. So it may deflect like this, it may deflect like that, it may deflect in a different manner. Now it depends on the cross section. Say if it is a rectangular section, say there is a column. Now if you calculate I in that direction you will get, I in that direction you will get. Now I about this is much higher compared to that. So here it will be I minimum, right. So if it is Ix, Iy, so Ix is greater than your Iy, so Iy will be taken here. Okay. So because if there is a thin plate, so it will buckle like this, not it will buckle like that, right. Or if it is a very arbitrary section, you have to find out which direction your I is minimum, number one. Number two, this L effective is very important. Now if there is a plate like this, now there might be a pin. So this hinge is hinge in that plane. Other plane it may be, say top end there is a support condition like this. There are two plates inside, it is there and there is a pin. So it can nicely rotate, but it can't rotate in that manner. So here if you take the bending in that manner, so it will be a fixed support more or less. So L effective will be 2L then. I may be less. So this side I may be less, but L effective may be more. Other end I may be more, L effective may be less. So different combination we may get, and from there we have to find out which side it will buckle, right. So there is a possibility it may vary, it may vary. If it is a ball socket type of joint, all the end it is identical situation. But if it is a plate type case, so one side it will be hinge, other side it will be clamped, right. So that part we have to remember. And there is a in the form of stress, if we write, this is one of the familiar, stress will be your P critical by A. So it will be pi square EI by L effective square, and here A. Now it is pi square E. Now this I if we take below, so I will come here. So we can say L effective by R square. So R is what? R is root over I by A. So its square means I will be there, I will go up, it will be A. So for a member, r is radius of gyration, and you have to take the minimum radius of gyration, right? And if it is minimum, this rather L effective by r is important. I was talking about r may be minimum this side, but L may be more. Other direction L may be say L and r, it may be in a reverse situation. So L by r, it is called a slenderness ratio. This is very important. So your allowable stress critical, it will be pi square EI by slenderness ratio square, and E for a particular material it will be fixed. This is the material property, Young's modulus, and pi square is fixed. So if we fix up steel, this part will be fixed. So it will be dependent on the slenderness ratio. What is slenderness ratio? It will be L effective by R. L effective is actual L into some factor 2 or 0.7, 0.5, 1, and R is your radius of gyration, root I by A. But not necessarily in one direction R may be minimum, but L effective may not be minimum. You have to check the different directions, and from there you will get a minimum L by R ratio. So that should be your guiding slenderness ratio, right? So L by R should be maximum. So when it will be maximum, this value will be large. So denominator large means your capacity will be less, right? So this is the basic guideline. Now we can carry out some problem in tutorial and try to explain how these parameters can be applied for designing a long column where length is quite high compared to the dimension of the member. So okay, we can complete here.